Welcome! In this session, we'll dive into problem number 1626 titled Best Team with No Conflicts. This problem challenges us to form the highest scoring team of players while ensuring there are no internal conflicts. We'll explore different approaches, analyze their complexities, and break the problem down step by step. Let's get started. In this problem, we're tasked with building the best possible basketball team while adhering to certain constraints. Each player is defined by their skill score and age, and a conflict arises if a player with a higher skill has a lower age than another player in the team. To solve this, we're given two arrays, scores and ages. The scores array represents the skill of each player, while the ages array represents their corresponding ages. The goal is to maximize the total score of the team while ensuring no conflicts occur. For example, if a younger player has a higher skill than an older teammate, that would create a conflict. The output will be an integer, representing the maximum possible score of a valid team that satisfies these conditions. Let's consider the first example to understand how this works. Here, the scores array is 1, 3, 5, 10, 15, and the ages array is 1, 2, 3, 4, 5. In this case, we can select all players because their ages are in ascending order, and their scores also increase or remain consistent with their ages. The team score is calculated by summing up the scores of all players, 1 plus 3 plus 5 plus 10 plus 15, which equals 34. This arrangement satisfies the no-conflict condition since the scores are non-decreasing with age. Now, take a look at a slightly more complex scenario. In this example, the scores array is 4, 5, 6, 5, and the ages array is 2, 1, 2, 1. The best team here includes players at indices 0, 2, and 3. This selection yields a team score of 4 plus 6 plus 5 is equal to 16. This combination avoids conflicts because the scores in the selected team remain consistent with the ages of the players. Including other players, or different combinations, would lead to a lower total score or introduce conflicts. In the third example, the scores array is 1, 2, 3, 5, and the ages array is 8, 9, 10, 1. Here, the best team consists of the players at indices 0, 1, and 2. This selection gives a team score of 1 plus 2 plus 3 is equal to 6. Player 3, despite having the highest score, cannot be included because their age is significantly lower, which would create a conflict with other players in the team. This illustrates the importance of carefully balancing scores and ages to maximize the team's score while adhering to the no-conflict condition. To solve this problem efficiently, we can sort the players based on their ages and scores. Once sorted, the problem can be reduced to finding the maximum possible team score using a variation of the longest increasing subsequence, alias, problem. This approach leverages dynamic programming to compute the optimal team score while ensuring that the no-conflict condition is satisfied. By structuring the solution this way, we can handle the constraints and large input sizes effectively. To tackle this problem, the brute force approach is the most intuitive starting point. The idea here is to explore all possible subsets of players and assess each one to see if it forms a valid team. A team is considered valid if it satisfies the condition that no younger player has a higher score than an older player. If a subset meets this condition, we then calculate its total score to determine the best possible team. However, the challenge with this approach lies in its computational feasibility. Since there are 2 to the power of n subsets for n players, the time complexity grows exponentially with the number of players. This makes the brute force method impractical for larger inputs, as it quickly becomes computationally expensive. While it might work for very small datasets, it's not a scalable solution for this problem. A more efficient solution leverages dynamic programming, which is based on the key observation that sorting the players can help eliminate conflicts. By sorting players first by age and then by score, we ensure that older players appear later in the list, and scores for players of the same age are in non-decreasing order. Once sorted, the problem reduces to finding the maximum sum of scores for a subsequence that satisfies the no-conflict condition. To achieve this, we define a DP array where DP, I, represents the maximum score of a valid team ending with the ith player in the sorted list. For each player, we look at all previous players to see if they can be part of the same team. If a previous player has a score less than or equal to the current player, we update the current DP state by adding their score. The final solution comes from the maximum value in this DP array. This approach has a time complexity of n squared, due to the nested iterations, but it's far more efficient than brute force. Additionally, we can optimize space usage by storing only the current and previous states in a 1D array, though this doesn't improve the runtime complexity. Given the problem's constraints and scalability requirements, we chose the optimized dynamic programming approach as the best strategy. The critical insight here is that sorting the players by age and score transforms the problem into a variation of the longest increasing subsequence problem, with scores replacing sequence lengths. This simplifies the structure of the problem and allows us to use a well-established DP technique to find the solution efficiently. The aha moment comes from realizing that the no-conflict condition aligns perfectly with checking for non-decreasing subsequences of scores after sorting. When comparing strategies, the brute force approach is clearly infeasible due to its exponential complexity, while the optimized DP solution strikes a balance between clarity, efficiency, and scalability. Space-optimized DP is a useful alternative for conserving memory but does not offer any runtime advantage. Therefore, the standard DP approach stands out as the most practical and effective choice, providing a structured and scalable solution to the problem. To solve this problem, we first need to clearly understand the requirements. The task is to select a group of players such that their combined score is maximized, but we must also ensure there are no conflicts among the players in the team. Conflicts mean certain players cannot be on the same team, so we need to carefully respect these constraints. Now, to represent the input, we use two main data structures. The first is an array called scores, where each index corresponds to a player's score. The second is an adjacency list called conflicts, which maps each player to a list of players they cannot be paired with. With these in place, we can start thinking about how to find the best team. A simple brute force approach is to generate all possible subsets of players. Using bit masking, we can represent each subset as a binary number, where each bit indicates whether a player is included. This gives us 2 to the power of n subsets for n players. Once we have generated all possible subsets of players, the next step is to validate each subset. For a subset to be valid, no two players in it should conflict with one another. To ensure this, we iterate through the players in the subset and check if any of their conflicting players are also present. If a conflict is found, the subset is discarded. For subsets that pass the validation, we then calculate their total score by summing the scores of all the players in the subset. Throughout this process, we maintain a variable called max_score, which tracks the highest score encountered so far. If the score of a valid subset exceeds the current max_score, we update it. Finally, after processing all subsets, the value of max_score is returned as the result. However, this brute force approach has significant computational costs. Generating all subsets requires 2 to the power of n iterations, and validating each subset can take up to n operations. This makes the time complexity 2 to the power of n*n, which becomes impractical for larger values of n. Additionally, the space complexity is determined by storing the conflict adjacency list, which uses n plus e space, where e is the number of conflict pairs. A key takeaway from this approach is the exponential growth of subsets as the number of players increases. With n players, there are 2 to the power of n possible subsets, so even for just 20 players, there would be over 1 million subsets to process. This demonstrates why the brute force method is computationally expensive and not scalable for larger inputs. However, the adjacency list representation of conflicts is a strength of this approach, as it allows us to efficiently check for conflicts by only querying directly related players. While the brute force method is guaranteed to find the optimal solution, it is clear that optimizations are necessary to handle larger inputs. Techniques like pruning invalid subsets early or leveraging dynamic programming could reduce redundant computations and improve efficiency. The key is to find ways to avoid generating and validating subsets that are clearly non-optimal. To achieve these optimizations, we rely on certain data structures and techniques. One such technique is bit masking, which provides a compact and efficient way to represent subsets of players. For example, with 3 players, the subset containing players 0 and 1 can be represented by the bitmask 011, while the subset containing players 1 and 2 is represented by 110. This representation makes it easy to iterate through subsets and check inclusion. Another important structure is the score tracker, a simple variable that keeps track of the maximum score encountered during the iteration. For example, we might initialize max_score to 0 and update it whenever a valid subset with a higher total score is found. These tools, combined with strategies like dynamic programming or greedy algorithms, can help us move beyond the brute force approach and find solutions more efficiently while still respecting the problem's constraints. In this solution, we aim to solve the problem best team with no conflicts using dynamic programming. The problem requires us to find the highest possible score of a team such that there are no conflicts, where conflicts depend on age and score relationships. First, we pair each player's age with their score, and sort the list of players by age first, and by score for players with the same age. This ensures that we can build a conflict-free team by iterating through the sorted list. We use a dynamic programming approach to solve this. The DP array is used to store the maximum score achievable for a team ending with each player. For each player I, we initialize their team's score to their own score, base case. Then, we iterate through all previous players j to check if adding player j to the team of player I would create a conflict. If there is no conflict, i.e., the score of player j is not greater than the score of player I, we update dp I to the maximum score achievable by including player j. Finally, the result is the maximum value in the DP array, which represents the highest score achievable for any team. This approach has a time complexity of n squared, where n is the number of players, making it efficient for the given problem constraints. Here, we start by importing the necessary classes and defining the solution class and the method bestTeamScore. The goal of this method is to calculate the highest possible score for a team that satisfies the no-conflict condition. To achieve this, we first determine the number of players, which is the length of the scores array. Next, we create a 2D array called players to pair each player's age with their score. This array is then sorted, prioritizing age in ascending order, and using scores as a tiebreaker if two players share the same age. Sorting ensures that we can build valid teams incrementally without violating the age and score constraints. After sorting, we initialize a DP array to store the highest possible score for teams that end with each specific player. We also declare max score to keep track of the overall maximum score across all players. The next steps involve iterating through the players. For each player, we begin with the base case where the team consists of only that player, so DP I is initialized to the player's score. Then, we compare the current player with all previous players to check if they can be included in the same team. If a previous player's score is less than or equal to the current player's score, the no-conflict condition is satisfied, and we update DP I to reflect the maximum score obtainable by including this player. Finally, we update max score to ensure it always reflects the highest score found so far. After completing the loop that calculates the maximum team scores for each player, we simply return max score, which now contains the highest score achievable for a team that satisfies the no-conflict condition. This return statement concludes the implementation of the method. By leveraging dynamic programming, we efficiently compute the solution to this problem while adhering to the constraints. The combination of sorting and dynamic programming ensures that the method is both optimal and easy to follow. To solve this problem, we start by combining the scores and ages into tuples, where each tuple represents a player. The tuples are sorted primarily by age, and in cases where ages are equal, by score. This ensures that as we iterate, we can maintain the no-conflicts condition. For our example, the sorted list of players becomes 7, 10, 8, 1, 9, 3, 10, 5. Next, we initialize a DP array to keep track of the maximum scores we can achieve for subsets of players. Initially, the DP array is set to 0, 0, 0, 0, meaning no scores have been computed yet. Now, we begin filling the DP array. For the first player, since there's only one, the score for this subset is simply the player's score, which is 10. So, DP 0 is updated to 10, and the DP array becomes 10, 0, 0, 0. Now, for the second player, we consider subsets that include players 0 and 1. The base case is to set DP 1 to the score of the second player, which is 1. Then, we check if the score of the previous player, 10, is less than or equal to the current player's score, 1. Since this condition is not satisfied, no update is made. The DP array remains 10, 1, 0, 0. Moving to the third player, we start by setting DP 2 to the player's score 3. We then compare it with the scores of previous players. First, player 0's score 10 is greater than 3, so no update is made. Then, player 1's score 1 is less than or equal to 3. This allows us to update DP 2 to the maximum of its current value in the sum of DP 1 and the current player's score, resulting in DP 2 equals 4. The DP array becomes 10, 1, 4, 0. For the fourth player, we follow the same process. We set DP 3 to 5 initially. Comparing with player 0, whose score is 10, no update is made since 10.5. Next, player 1's score satisfies the condition, updating DP 3 to 6. Finally, player 2's score also satisfies the condition, updating DP 3 to 9. The DP array is now 10, 1, 4, 9. At this point, we can determine the result for the first example. The maximum value in the DP array represents the highest score we can achieve while satisfying the no conflicts condition. For this example, the maximum value in DP is 10. Moving to the second example, where scores equals 4, 5, 6, 5, and ages equals 2, 1, 2, 1, we begin by combining and sorting the players. The resulting list is 1, 5, 1, 5, 2, 4, 2, 6. We initialize the DP array as 0, 0, 0, 0, and proceed to populate it. For the first player, the score is 5, so DP 0 is updated to 5. The DP array becomes 5, 0, 0, 0. For the second player, the base case sets DP 1 to 5. Comparing with player 0, we see that their scores are equal, so we update DP 1 to 10, which is the sum of DP 0 and the current player's score. The DP array is now 5, 10, 0, 0. For the third player, we start by setting DP 2 to the player's score, which is 4. Comparing with player 0, we find that the condition is not satisfied since player 0's score is greater than 4. The same is true for player 1, so no updates are made. The DP array remains 5, 10, 4, 0. For the fourth player, we set DP 3 to 6. Comparing with player 0, we find that the condition is satisfied, allowing us to update DP 3 to 11. Then, comparing with player 1, the condition is satisfied again, updating DP 3 to 16. Player 2's score is less than or equal to 6, but no further update is needed. The final DP array becomes 5, 10, 4, 16. The maximum value in DP is 16, which is the result for this example. This concludes the walkthrough of the solution, where we use dynamic programming to maximize scores while ensuring no conflicts based on the given conditions. In analyzing the time complexity of our solution, we begin with the sorting step. Here, we use the sorted function to arrange the players by their ages, and in cases where ages are the same, we fall back on sorting by scores. This sorting involves a list of size n, where n is the number of players, and the operation takes O, n log n, time. Following this, we initialize the dynamic programming table, which is represented by the DP array. This array has a size equal to the number of players, so initializing it with zeros is a straightforward O, n operation. These two steps form the foundation of our solution, preparing the data for the dynamic programming process that follows. Next, we delve into the nested loops that handle the state transitions in dynamic programming. The outer loop iterates through each player from index I equals 0 to I equals n1, giving us O, n iterations. For each player, there's an inner loop that goes through all prior players, from j equals 0 to j equals I1. This results in a triangular summation of iterations across all players, which simplifies to n1 asterisk n/2, or O, n squared, in asymptotic terms. Inside the inner loop, we perform a comparison to check if a player can be added to the team without conflict, and we update the DP array accordingly. Both of these operations are O1. Finally, after filling the DP array, we find the maximum value in it using the max DP operation, which takes O(n). When we combine these steps, the overall time complexity for the solution becomes O(n log n) for sorting, O(n squared) for the nested loops, and O(n) for finding the maximum, with the quadratic term dominating. With the time complexity established as O(n squared), let's now analyze the space complexity. The input lists, ages and scores, each have n elements, but since they are provided as input, they don't count toward additional space usage. The first auxiliary array is the player's array, which holds the sorted list of tuples, age, score. This array requires O(n) space because it has one entry for each player. Similarly, the DP array, which maintains the best team scores for each player, also requires O(n) space. Beyond these, we use a few loop indices like I and j and some temporary variables for comparisons, all of which contribute only O(1) space. When we combine these components, the total space complexity of the solution sums up to O(n). To put everything into perspective, let's compare the dynamic programming approach to the brute force method. A naive solution would involve generating all possible subsets of players, checking each subset for conflicts, and calculating the sum of scores for valid subsets. Generating all subsets requires 2 to the power of n combinations, and checking each subset for conflicts could take up to O(n) time, leading to a total time complexity of O(n*2 to the power of n. This exponential growth is inefficient and impractical for large inputs. In contrast, the dynamic programming approach avoids generating subsets altogether, focusing instead on building optimal solutions incrementally. This reduces the time complexity to O(n², a significant improvement that makes the solution scalable for inputs as large as n equals 10⁻3. In summary, the dynamic programming solution achieves a time complexity of O(n², and a space complexity of O(n), making it far more efficient and feasible than the brute force alternative. When tackling this problem, it's important to be mindful of common mistakes that can derail your solution. First, failing to consider edge cases is a frequent pitfall. For instance, if the input is empty, contains only one element, or reaches its maximum constraints, your code might break or become inefficient. A brute force approach, for example, could time out if the input size is very large, like 10 to the power of 5. Addressing edge cases early ensures your solution is robust. Another mistake is improper handling of duplicates. This is particularly relevant in problems involving arrays or subsets. Failing to account for duplicates can lead to redundant computations, such as generating the same subset multiple times, which then requires additional filtering. Overcomplicating the solution is another trap. Sometimes candidates try to implement overly complex optimizations without thoroughly understanding the problem constraints, which can introduce bugs and inefficiencies. It's always best to start with a clear and simple approach before refining it. Lastly, neglecting to analyze time and space complexity is a major oversight. If your solution is computationally expensive, like O(2 to the power of n), for subset generation, it might fail for large inputs. Always evaluate the feasibility of your approach in terms of scalability. Now, missing base cases in recursion is another common issue. In recursive solutions, it's essential to define clear stopping conditions. Without these, your code might result in infinite recursion or yield incorrect results. Shifting to interview strategies, pattern recognition is a key skill. Many problems share underlying patterns, such as divide and conquer, dynamic programming, or backtracking. Identifying these early can help you select the most efficient approach. Additionally, clear communication is crucial during interviews. Walk the interviewer through your thought process step by step. Even if you start with a brute force method, explaining its limitations and how you plan to optimize it demonstrates strong analytical skills. Optimization should be iterative. Begin with a straightforward solution, even if it's inefficient, and then refine it. For example, you might move from O(n²) complexity to O(n log n), or even O(n). Lastly, always test your solution with a variety of cases, including edge cases and large inputs. Discussing these tests in the interview shows thoroughness and attention to detail. There are also related problems that can help you build a stronger foundation. Examples include LeetCode 78 for subset generation, LeetCode 39 for combination sum, LeetCode 46 for permutations, and LeetCode 416 for partitioning subsets with equal sums. Each of these problems reinforces concepts relevant to this challenge. When considering alternative approaches, brute force is often the simplest to implement but becomes inefficient for large inputs. It's a good starting point for small constraints but not scalable. Backtracking, on the other hand, is highly effective for problems involving combinations or permutations, though it requires careful pruning to avoid unnecessary computations. Dynamic programming is an excellent choice for problems with overlapping subproblems, offering better efficiency at the cost of additional space. Finally, greedy algorithms can be quick and simple when local optimality leads to a global solution, but they're not always applicable, so it's crucial to verify their correctness. Choosing the right approach often involves weighing these trade-offs based on the problem's constraints and requirements. Great job staying with us until the end. To summarize, we tackled problem number 1626 using dynamic programming and analyzed its complexities. We also highlighted some key takeaways about optimization and problem-solving strategies. Thanks for watching, and don't forget to like, share, and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!